In this video, I'd like to talk about chiral molecules and enantiomers. So we've already encountered stereoisomerism, but as a reminder, when we have molecules with the same molecular formula and they're connected to the same atoms, but they have different spatial orientations, we would call those molecules stereoisomers. Cis and trans is one type of stereoisomers that we've already seen. We're going to look at another type of stereoisomerism in this video, and there's sort of two key points to our discussion. One is chirality. And so any object that is not identical to its mirror image is said to be chiral. And another important thing that we need to consider is that one way to tell whether two objects are identical or not is to determine whether they're superimposable, right? Whether I can set one essentially on top of the other and they fit perfectly. If they're not superimposable, then they're not identical. So for some everyday examples of chirality, these sunglasses are identical to their mirror image, right? If I was to pick this up and it was like a hologram, I could fit it exactly over the original pair of glasses. And so these sunglasses are superimposable on their mirror image, and so they are identical. So the object is identical to its mirror image, and therefore it is said to be achiral. When something is chiral, it is not identical to its mirror image, right? So if I consider this right-hand glove, its mirror image is a left-hand glove, and while they look very similar, we know they're not identical, right? If you try to put your left hand into the right-hand glove, it doesn't work. And so because a right-handed glove is not identical to its mirror image, we would say that it's chiral. Now, any three-dimensional object can be classified as being chiral or achiral, and since molecules are three-dimensional objects, they can also be characterized as chiral or achiral. Now, if we have a large complex molecule, it can be very difficult to tell just by looking at it whether it's chiral or achiral. Thankfully, we have an easy way to tell. So chirality occurs most often in molecules that have a tetrahedral carbon that is bonded to four different groups, right? So this carbon is attached to, right, a red, a blue, a green, and a white atom, right? And so it's connected to four different groups. And so when we take its mirror image, they are not identical to one another. And it might help if I go to this other program, right? So here I have two similar molecules to what I had in the PowerPoint presentation, right? And the right-hand molecule is the mirror image of the left-hand molecule. If we imagine putting a mirror right down the center of the screen here, right? And so if I try to superimpose these on top of each other, right? So essentially I try to uh, rotate one of the molecules so that it's identical to the next one, right? When I do it like this, right, I can sort of get the blue lined up, but the red lined up, but the white and the green are sort of in the wrong places, right? If I try to twist it around and see if there's some way that I can make it so that the molecule on the right is identical to the molecule on the left, I can't do it. And so while they're mirror images, they're not identical to each other. So we would say that this molecule is chiral. And this one is not identical to its mirror image, so it is chiral as well. And just a bit of terminology. The IUPAC term for carbon bonded to four different groups is called a chirality center. I think more commonly you'll hear the terms chiral center or stereocenter for a carbon that's connected to four different groups. So let's take a look at a couple molecules and see if we can find all of the chiral centers. So uh, oftentimes we're doing this with line bond structures, and it can be kind of hard to tell because we have to remember, right, that there are hydrogens attached to these. So it can often be useful to go ahead and put in the hydrogen so we can see more clearly what we're looking at. Right, and so any carbon that's connected to three hydrogens is not going to be a chiral center, right? Because this carbon is connected to, three hydrogens, right? Those three hydrogens are identical. Also, any CH2 groups are not going to be chiral centers because it's connected to two hydrogens. So our options for chiral centers really are this carbon, and this carbon. If I look at the one on the left, right, it's connected to two CH3 groups, right? So it's got a hydrogen, it's got this mess, but the two CH3 groups are identical, and so this is not a chiral center. if I look at the carbon here, it's got a methyl, it has a hydrogen, it has an isopropyl, and then I guess this is a sec-butyl group, right? So all four of those are different. I've got a hydrogen, isopropyl, methyl, and sec-butyl, and so this one is a chiral center. I guess I went out of order here, but this one is too, right? It's got a hydrogen, it's got a methyl, it's got an ethyl, and it's got this group here, right? All four groups are different, so this molecule has two chiral centers. And when a molecule has a chiral center, it's going to be chiral. When I look at this example, I'm not going to put the hydrogens in, right? But we know, right, I've got a CH2 here, a CH2 here, a CH2 here, a CH2 here, a CH2 here. So, right, none of those are going to be chiral centers. Now, this one here is a little bit more interesting. So I have a hydrogen and I have a fluorine, but what about the ring? How does it count? Well, we sort of look at going clockwise and counterclockwise around the ring as being two different groups. And so if I encounter the same atoms when I go clockwise as when I go counterclockwise, then we would say those two groups are identical and the molecule is not going to, or that carbon is not going to have a chiral center, right? So when I go clockwise, right, I've got CH2, 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 and I'm back where I started. Counterclockwise, I get the same things. And so that would not be a chiral center. And so if a molecule doesn't have any chiral centers, then the overall molecule is achiral. Right, when I look at this one, right, I've got CH2s here and here and here and here. So none of those can be chiral centers. If I consider this carbon again, right, when I go clockwise, right, so I've got an F and an H, so that's two. And then when I go clockwise, right, I get a CH2 and then, right, not a CH2. When I go counterclockwise, right, CH2, CH2, right? So at the second position, they differ. So the group going clockwise is different from the group going counterclockwise. So these count as two different groups. And so that is going to be a chiral center. We can check and see if we have any more. Right, I think this carbon, right, so it's got a hydrogen, it's got this mess, and then when I go counterclockwise, it's not the same as going clockwise, so this would also be a chiral center. I think this carbon is out. It's got two hydrogens, right, and this one has, right, an OH and a carbon, and an OH and a hydrogen, and then this big ring, so it has four different groups, so that would be a chiral center as well. All right, when I look at this molecule, right, I can immediately eliminate. I've got a CH3, a CH2, a CH3, a CH3. Right, this carbon has two methyls, so it's out. If I look at this carbon, right, I have an ethyl, an isopropyl, a hydrogen, and then this mess. So I think that's going to be a chiral center. When I look down here, on the benzene ring here, right, this is not sp3 hybridized. So none of these guys that have the double bonds can be a chiral center. Right, this carbon also with a double bond, it's not sp3 hybridized. It can't be a chiral center. It's not tetrahedral. Right, my other option is this. Right, I've got an OH, a hydrogen, and then going around the ring is not identical clockwise and counterclockwise. So I think I have two chiral centers. Three chiral centers in this molecule. All right, now another bit of terminology. When a molecule is chiral, it will have one non-superimposable mirror image, and that is called its enantiomer. And then the two compounds together are said to be a pair of enantiomers, right? So this molecule has a chiral center, right? I've got the chlorine, I've got the methyl, the ethyl, and a hydrogen. And so this is a chiral center, so the molecule is chiral. So it is not identical to its mirror image. So because it's a chiral compound, its mirror image is said to be its enantiomer. Now, when we're given a molecule, sometimes we want to draw the enantiomer. The easiest way by far to do that is to just draw the identical molecule, and then whether I have a wedge saying it's coming out towards me, replace that with a dash. So if I wanted to draw the enantiomer of this molecule, right, all of these guys in the plane are the same. All I need to do is change the wedge to the dash. Same thing here. I have one wedge to draw the enantiomer. I would just draw the dash. Now, one key point, if I have this molecule, inverting wedges and dashes doesn't create a new molecule like it does in chiral compounds, because right, this carbon is not a chiral center. It's got two methyl groups, so these are in fact identical molecules. It's only when we have chiral molecules that have chiral centers that we have enantiomers, where the mirror images are different from the original molecule. So oftentimes students ask at this point, why do we care about chiral molecules? Well, they are in fact different compounds with different chemical properties. One example is ibuprofen, which has a chiral center here. Um, it turns out its enantiomer is a different compound, and while ibuprofen S, and we'll talk about what the R and S designations mean in another video, this enantiomer is active, this enantiomer is not. So uh, another example, uh, naproxen, which is another pain reliever. This enantiomer is a liver toxin, and this enantiomer is active. So it's important to know which of the two enantiomers we have, certainly in the pharmaceutical industry, because we don't want to be giving people a liver toxin when we think we're giving them a painkiller.